In a recent video, Steve Mould was talking about autoparametric resonances. In passing, he mentioned that he thought about making an autoparametric swing, but that the springs that he'd have to use would be garage door springs, and when you stretch those, they store a lot of energy. If they broke, it could be dangerous to whoever's on the swing. While garage door springs do indeed store a great deal of energy, it's actually the older variety that coil or twist as you open the garage door that store the most energy. Newer garage doors use linear springs instead of torsional springs. While those store energy, of course, they don't store nearly as much as the torsional springs. So I was interested in seeing what kind of spring you would need to make an autoparametric swing, so I started doing a little analysis. Here's an idealized version of an autoparametric swing. You have the chain here, which is elastic, so there's a spring in the chain, so the person can move along this direction and also swing in this way. So that's just a simple model of an autoparametric swing. The two coordinates, y and theta, are actually coupled in this because the equation that governs theta depends on this length here, and that length depends on y. To do a simple analysis, though, you can decouple these into just a degree of freedom where the person is bouncing up and down, and then another degree of freedom where the person is swinging. This will give us an estimate of what kind of spring constant we need here. It's not going to show us how the autoparametric resonance will be achieved, but it will give us some design guidelines. The equation governing the motion of the y-coordinate is my double dot, mass times acceleration, plus k, the spring constant here, k, y equals 0. The equation governing the motion of the pendulum, or the swinging, is L theta double dot, the angular acceleration, plus g theta equals 0. We can rewrite these as y double dot plus k over m y equals 0, and theta double dot plus g over L theta equals 0. These terms here govern how fast the oscillations are. In fact, these are the natural frequencies of the system squared. So we'll have omega y, which is the bouncing natural frequency, and that is the square root of k over m. Omega theta, the swinging natural frequency, is the square root of g over L. So that's the natural frequency of a pendulum. For an autoparametric resonance to occur, we need omega y to be equal to twice omega theta. So that gives us square root of k over m equals 2 times square root of g over L. Squaring both sides, we get k over m equals 4 times g over L. Or equivalently, k equals 4 mg over L. And we recognize this is just the weight of the person on the swing. One problem that you have when you want to oscillate a person at a low frequency is this static deflection of the spring. Remember, this system is under the influence of gravity. If we look at the forces right here where the spring attaches to the seat with the person on it, that the force in the spring has to equal the weight of the person and the seat. But that means that this spring is already stretched. So if we could unstretch the spring, we would have to put a force here to hold the person up. So now this spring is not stretched. The force in the spring is 0, and it's this force here that's counteracting the weight of the person. Now, the problem comes because we want this to have a very low natural frequency. Say we want to have this thing go through one oscillation in 1 second. So that would be the period equals 1 second. And that says that the linear frequency is 1 over that period, which is 1 hertz. And that says that the angular frequency is 2 pi radians per second. From before, we know that omega y is the square root of k over m. And that is equal to, in this case, we want that to be 2 pi. This then tells us that k equals 4 pi squared times the mass. Now, if we look at this system here, and again, this is just statics. So all this person is just hanging statically from this spring. And we want to figure out how much the spring stretched when the person started hanging from it. The static problem says that k times the change in length, which is the force in the spring, must equal the weight of the person hanging from it. Or equivalently, the change in length of the spring equals the weight of the person divided by the spring constant. That gives us that delta L equals mg all over 4 pi squared m. So our m's cancel out nicely, and we get g over 4 pi squared. Well, pi squared is 9 point something, and G is 9.8 something. So to say roughly these two things cancel out. So the change in length of our spring is approximately 1/4 of a meter, or 25 centimeters. And that's quite a large change in length for the spring. So we need to stretch it 25 centimeters to have a person be able to bounce up and down at 1 hertz on it. And that's part of the problem with this. You have this very large static deflection of the spring, and you store a lot of energy in there. The energy stored in the spring is 1/2 K delta L squared. Substituting in for delta L, we have 1/2 M squared G squared all over K. So that tells us how much energy is stored in the spring. Let's say Steve is 80 kilograms, which is probably an overestimate, but you can always add weight to a person, and it's very difficult to subtract weight from a person. So an overestimate's good here. That tells us that the spring constant, K, would be 80 times 4 times pi squared. Now let's say that pi squared is roughly 10. So that's 3,200 newtons per meter is the spring constant that we need. We then can get an approximation for the energy stored. So we have 1/2 times 80 squared times, we'll say G squared is roughly 100 over 3,200. Now this cancels with those two zeros. 80 squared is 6,400. So we get 6,400 divided by 64. And that is simply 100 joules of energy, which is actually not a lot. A joule is a watt second. This is how much energy a 100-watt light bulb would use in 1 second. Now let's go back to our original system that we were looking at for an autoparametric resonance to occur. So again, we know that for that autoparametric resonance, we need K over M to equal 4 times G over L. So you want to get an estimate of what values of L would be feasible. To do that, let's say that the swing takes 3 seconds to go through 1 cycle. So that is a period for the swing, T theta, of 3 seconds. That gives us a linear frequency, F theta, equals 1/3 hertz, and that gives us an angular frequency, omega theta, equals 2 pi all over 3 radians per second. And we use an approximation as just 2 radians per second, as pi is very close to 3. That frequency equals square root of G over L. So we know that if we square both sides, we get 4 equals G over L, or L is to be G over 4. And if G is roughly 10, then that's 5/2, or 2.5 meters. Obviously, it's going to be changing because we actually have this system here. But to have a period of 3 seconds, we need this to be 2.5 meters. Now, that doesn't mean that the spring has to be 2.5 meters. So that's the length here. That's kind of the nominal length here. So we want a spring, and the maximum length of the spring would be 2 meters. So we'll say that that tells us that the spring length is roughly 2 meters. For the autoparametric resonance to occur, we know that K needs to be equal to 4 mg all over L. And if we assume that the mass is 80 kilograms again, that winds up being 4 times 80 times, again, roughly 10, divided by L, which is 5/2. So let's see what we get here. That cancels with this, and that becomes a 2. And then, let's see here, we wind up with 16 times 80. And that is equal to, let's see what we get, 16 times 80 equals 1,280 Newton per meter. So that's the spring stiffness that we need. So it's not actually a very stiff spring. So how much energy would be stored if we just hung from this spring statically? So remember that the energy we derived was 1/2 m squared g squared over k. So we wind up with 1/2, and again, if m is 80, that's 6,400, and then g is roughly 10, so g squared is 100, divided by 1,280. We can cancel this out. That becomes 50. We wind up with 64,000 times 50 divided by 1,280. That gives us 250. So we have 250 joules of energy stored in that spring. Now, you have to remember that this is actually two springs, so there would be half of that, 125 joules of energy stored in each one of the springs. So I think it's actually pretty feasible for Steve to build something like this. We can also figure out what the change in length of the spring would be. And so the change in length, remember, it was the weight of the person divided by the spring constant. So if the weight of the person is roughly 800 newtons, and we divide that by the spring constant, 1,280 newtons per meter, we have 800 divided by 1,280, or 0.625 meters, or 62.5 centimeters. So that's quite a bit of stretch. We want the final length of the pendulum arm here to be 2.5 meters. So we want the whole system, the spring and whatever chains are attached to it, to be roughly 2 meters before the person gets on the seat. So for an autoparametric resonant swing, we need two springs to have a spring stiffness of 1,280 newtons per meter. So each spring needs to have a spring constant of 640 newtons per meter. So we can go to McMaster Carr and we can search for springs and see all the springs that they have. So we have compression springs. That's not what we want. We have extension springs, but these are very light springs, kind of for using in consumer products and things. These aren't industrial strength springs or garage door springs. So you can go down, keep scrolling down here until you get to die springs. So we look at what kind of die spring stock we have available to us. And if we scroll here, we can look and see what spring rates they have available. These are in pounds per inch because, of course, McMaster Carr is in the United States. So 640 newtons per meter is about 3.6 pounds per inch. And we can see that actually we have a kind of a gap there. So I guess the closest we could do would be this 2.95 pounds per inch. So pick that spring. And we can see that we can get these in, the lengths are 1 meter, 1 yard, 36 inches. So that's, roughly a meter long. And they cost about $36 each. Getting two of them, Steve would have to spend about $73 to get two of them. They have two diameters listed. The outside diameter, which would be basically if you wanted to put this thing in a hole. So that is 7/16 of an inch. And the shaft diameter, which is if you want to put a shaft through it, is 1/4 of an inch. So springs like this exist. We don't have the exact spring rate that we wanted, but we can take this spring rate and go back and see what kind of performance the autoparametric swing would have with this spring. Now, we only have roughly 1 meter lengths, and we could have up to 2 meters. This is okay. So we have 1 meter, and we need it to stretch about a half a meter extra. So if we come back and try to sketch out a simple design for this, we would have whatever the swing is attached to here. So we'd have one cord here, and then another cord here, and they would have springs in the middle of them. Then we'd have our seat for our swing. We want this to be roughly 2 meters. And in that, we have roughly 1 meter of spring. Then when somebody sits on the swing, this spring will stretch to about 1.5 meters, and this will be about 2.5 meters here. So how would we make this to make it safe? Well, the idea I have is to take one of these springs. So we have the chain and then the spring here, then chain, and to just encase it in some PVC pipe. So get some PVC pipe that's big enough that would go over it, and obviously extend down farther enough so that even when it's stretched, the chain is inside of the PVC pipe. So we have the PVC pipe over it. Then we put a cap on the end of it here and drill a hole in the cap, and so that the chain could go through. And we could actually put a cap down here so the chain could go through there. You need to hold the swing, the ropes of the swing. And so the PVC pipe, if you have this encased in PVC here, and this encased in PVC here, that would give you a place to hold on to the swing. And obviously we would need this in this region here, to slip in and out. So we'd have to make a big enough hole so that this could go in and out of so the chain could come in and out of the PVC tube. And since there really isn't a whole lot of energy stored in these springs, I think, if you get a decently thick-walled PVC pipe and caps, it would be extremely safe. I can't imagine there's not enough energy stored in here to break this PVC. I wish I had the resources at the moment to do it, but I don't, so I leave that to Steve.